All right, so here in this video lecture, let's learn how we can apply our understanding of taking definite integral into finding the length of an arc right here. Or so for short, our discussion title here is called arc length. Okay, so the whole idea is as following, and allow me to erase the title here so that I can maximize my board space right here. So at this point in your mathematical experience, then you have seen a lot of different graphs, and a lot of those graphs are in bent shape. Okay, like say your y equals x squared curve is a bent parabola shape like that. Okay, and then your y equals 1 over x, the graph here is a bent shape right here. Okay, so the idea now is that with any of these graphs right here, any piece of any of these graphs right here, we can restrict that into a certain portion, and there we have an arc. Okay, so this parabola over here, I can just take that one portion right here, and this is an arc, and we now learn how to calculate how long that arc is. So it's bent, but imagine if we straighten it out, how much length is that going to be? So we're talking about the physical length if we trace around the curve like that. Okay, so the curve is being curved, being bent, but now we restrict that into a certain window. Okay, in a certain window, and then we have an arc, and that's what it is. And then now think about if we straighten it out. I mean, we don't really physically straighten it out, but if we would straighten it out, then what would be the length of that arc right there? Okay, and that's what we're learning to find out right there. Okay, and so of course the idea now is to use calculus into finding the length of the arc. So let me now describe the major idea right here, the major characteristic of the problem like that, or as a planning, how we derive the later formulas and all that. So this problem here, this kind of application, we will have a definite formula to use. So here's an arc. Think about that. This is a piece, one piece of, or a piece of any graph so you have your graph f of x, or whatever that is, and then we're going to restrict it in an interval. And so here we simply have an arc. And so now I have to also be clear, the graph we see here could be the graph of some function f of x, or the same graph can also be thought of as a sum function in terms of y right here. That's one thing for clear, because in the end it's just a physical curve. Okay, it's a physical graph right there, so it could be expressed as a function of x, or the same graph here could be expressed as a function of y. Okay, so either way we're gonna be ready for both. So just now, without any worry about the expression in terms of x or the expression in terms of y right here, here's how we plan to find the length of this arc, the physical length of that arc. Well, the idea is as following, and this is starts, okay, and at some start and to some end of the curve. And so the idea now is that we think about breaking the arc into subsections, okay, and then there between these subsections right here, we're going to draw a straight line. Okay, we draw a straight line, and of course forgive me if I cannot make the precise picture here, and I cannot make the clear distinguishment between straight line and curve anymore, because with these subsections here, it's already close enough to the curve shape like that. Okay, but each one of these is short segments here. Each one of these subsections there, we're gonna take those as straight segments. Okay, and so those straight segments right there, each one of these sub-segments right here, I'm gonna call them, it's a distance ds. Okay, it's a distance ds. It's a small little section right there. So this is a ds between these two tick marks right here. This is a ds. Okay, and so now, just very similar to the idea of the Riemann sum, then the smaller those ds that we break it down, right, then the better approximates we get to the complete length of the full length of that arc right there. Okay, so now in that way, the journey starts from here. I have to remind anybody, an integral is accumulation. An integral is accumulation. Okay, and so we are about to apply, as I said earlier in the beginning of this lesson right here, we apply our integral, our understanding of the definite integral into calculating the length of an arc. So that means what are we accumulating here? So in order to achieve the total length of this arc, I am going to be accumulating all of the little lengths here, little ds. Okay, each of those ds here is a straight segment that's close enough to the actual piece of arc there. Okay, and so we're going to be accumulating all of those ds. So think about this. Eventually, all of the ds is going to get infinitesimally small, so that there's no difference anymore between the arc in that little subsection with the ds anymore. And then we're accumulating all of those differential infinitesimally small ds from the beginning to an end. Okay, from a start to an end. All right, so keep accumulating all of those ds's like that. And that's how we get to the length of the arc. We call it capital L. So this is the only fundamental for the whole discussion here, for the entire lecture here that we're doing. Okay, we're accumulating all of the little ds segments. All right, so now allow me to write this formula on that little space here, because I need more space to do some more deriving work. How's that? Okay, so the length, any length, is accumulation of all the little ds from start to end. And so now hopefully you just simply understand what that ds is. There's no special calculation yet. It's just we break the curve, our arc, into as many subsections as possible. In each of those subsections there, we produce a small segment. And so those are the ds. And so the more subsections, the ds become smaller and smaller, infinitesimally small, to the point that see, straight segments and arc will become close with each other. Okay, so now let's look even a little further into the ds right here. So now it's a ds, and this is sort of like a really zoomed in and magnified version. Let's say in one section right there, in one section for one ds, as a straight section. Then as far as a triangle, there's in the way how we have that distance ds right here, then there's a change in y, and it's a dy here. And the reason I'm not using delta y, but instead I'm using dy here, is because think about it. This ds right now, it's a big version of the ds, but the idea now is we letting ds get infinitesimally small. So ds itself is a differential, and so it's related with the dy differential. And it's also related with the dx differential, because when the ds is so small, then each one of the dy dx become infinitesimally small as well. And so there at that level, being microscopic level, that way, then dy and dx are all the differentials, the dx dy differentials like that. Okay, and so in this, but definitely my point I'm trying to show everybody here is that we're having a right triangular setting right there. Okay, and so in that way, Pythagorean theorem, which everybody knows by heart, that Pythagorean theorem says ds as the hypotenuse of this triangle, ds square, okay, equals the dy all squared, that differential square. So surprisingly, even at that differential level, that microscopic level, we're still going to be able to use the Pythagorean theorem plus dx all squared. So this is a truth that's permanently true right there. Okay, no matter at how scale your level is or how tiny your level is. Okay, and so now once we've had that, then I'm going to derive a further result. So ds itself is a square root, and everything here now we're talking about length, and so it has to be positive, because I keep reminding my algebra students, I keep reminding any of my students algebraically that anytime we take the square root of both sides, it has to be a plus or minus square roots. But here in our application, we're looking for the positive square root, because ds here makes sense to be a positive quantity. So I'm looking for a positive square root. So here we're looking at dy square, okay, plus dx square, okay, all square. And that's the expression. So ultimately, ds is this expression. The square root of dy squared, the differential dy squared plus the differential dx squared. That's how we express ds. All right, so why am I mentioning about this? So now so I'm going to leave this here, allow me to move on to the other board. So now two scenarios can happen, as I mentioned earlier. This same curve right here, that same arc right here, we broke that down into infinitely many subsections, right? And each of those is a ds. So there's a ds right here. And then the more we break it down, the more ds we break it down, the finer it is, and the better approximates. And that's why in the end, this is the total accumulation of all ds from a start to an end. So I pointed it out earlier that a curve, now in this problem, this kind of problem, any curve is just a curve, a physical drawing. And the curve there as a graph can be expressed, can be represented as a function in terms of x, okay? Or the same curve can be represented as a function in terms of y. That's what I said earlier. And now let's push it into that way. The same curve can be regarded as a function of x, or can also be regarded as a function of y. Okay, so now if we put the axes on, that's what it is. So if this is the curve expressed as a function of x, then the start point happens start and end happens between an interval on the x-axis. I'm talking about if our curve here is represented as a function in terms of x, then the start point and the end point on the x-axis is some value a on the x-axis to some value b on the x-axis. Okay, and then similarly, the same curve here, okay, if we represent the curve as a function of y, then on the y-axis, starting is going to be some y value at c to some y value at d. Okay, so we have two ways. Any curve, we always have two ways to represent our curve, either in terms of x or either in terms of y. Okay, and that all depends on our application. Okay, so in this way, because of that, so now with this accumulation right here, now clearly speaking, it equals to the accumulation from start to end. Allow me not to rush into the writing down what the start and end yet, but each ds, according to what I have derived on the other board, each ds here is a square root of a dy square plus dx square. Okay, and you have seen all of that logical reasoning, and so that means generally any length has to be the accumulation of all these square root expressions, because it's ds, and each ds here is dx square plus dy square. I'm reordering the order of these two differentials a little bit inside my square root, but that should not matter. Adding is commutative. Okay, so now we have this ds, and so now from this, algebraically, now we can't get away from the algebra. Okay, so again, you got to get your algebra going. So from this expression, which generally represents the way to find arc length for any arc, then I have a choice. Now as I'm saying it clearly, I have a choice. You see that there's a dx squared plus dy squared. Algebraically, I have a choice to factor out. So here I'm going to choose to factor out dx squared. So inside of my square root, I'm factoring out the dx squared. Okay, so factoring out the dx squared, let's see what's happening. It's going to give me the following. Well, after we pull out that dx squared, then in parentheses I have a 1, because factoring out that, the remaining factor is a 1. Now factoring out the dx in this term, where we didn't see dx originally. Okay, but now see, that's why algebra is extremely important. Now factoring out the dx, and that means we're looking at dy squared over a dx squared. Okay, and then this is a start to an end. So it's a sort of like a further derived form of that. And I said from here to here is a choice. Okay, it's a choice. And so in this way, now it's a product between the dx squared and the 1 plus the dy squared over dx squared right there. Okay, and have a closer observation of this, because in my next step I'm going to talk about that. So now here being a product, I can pull that dx squared outside of the square root. And so again, algebraically, as we pull a factor outside of the square root, then that factor is going to get reduced with the square. So here it's already square, so outside of the square root it's going to be just dx. All right, so now I'm looking at the square root of 1 plus. Now this dy squared over dx squared really is the dy dx square. Okay, and then my dx now as a product being placed here outside the square root. Let's not be too worried about the start and end yet. So I still have that start here, okay, and I still have that end here. But let's observe this formula right here. Let's see what we have right here. The expression here is a dx, and it's a square root expression, and it's a dy dx. What does a dy dx look like? The dy dx here is our lovely symbol for, it's now a ratio. Okay, but at some point earlier we have already learned that now a ratio dy dx is also means, it's understood the same as the derivative symbol. The derivative symbol is not only the derivative symbol. The derivative here, it's read the derivative of the function of this curve here expressed as a function y in terms of x. A function in terms of x. Y as a function in terms of x. So dy dx reads the derivative of the function y as a function in terms of x. But see, it was also understood as the ratio of the two differentials dy over dx. And so now we realize, hey, if this is a ratio of the two differentials dy over dx, then that is the same as the derivative of the function y in terms of x being square. So that means this is expectedly or tentatively an expression of x. So what's the good usefulness of this? This means now this formula here, we arrived at a formula where we can calculate the arc length, the length of this arc. If we want to do the calculation of the integration, if we want to proceed with the integration in terms of x, Okay, so that's one option. So if that's the case, yes, like I said, everything is in terms of x. We are integrating in respect to x. So that means the curve here must also be expressed as a function of x right here. And so if the curve is expressed as a function of x, then now look at the picture right here. Then in that picture, our starting point happens when x equals a on this interval, and our ending point of the curve happens when x equals b on the x-axis. And so now from that point in that logic right here, I can now go ahead and I can now finalize start and end by from a to b. Ladies and gentlemen, arc length for any curve can be found by this formula. If we want, as a choice, if we want to integrate in respect to x or along the x-axis, then that means in our responsibility we have to express the curve as a function of x, and then do the dx thing in here, and then find the derivative of the function of x, dy dx, and then put that in this formula. And then the interval will of course be, the start to the end will of course be expressed in terms of x. This is the x equals a on the x-axis. This is x equals b on the x-axis. So that's one way. Okay. You can go ahead and pause the video to take notes and see how I arrived at. See how I derived that. But now I am going to, assuming you already had some notes taken, and pause the video. Now I'm going to erase this. What if we had a different choice? Like I said, the reason we arrived here was just simply as a choice. So sometimes the same expression here, let's roll back to this point. I have no hesitation at all to erase everything we did, because it could have been a different choice. Right from this point right here, we know by heart that our ds equals the square root of dx squared plus dy squared. Okay, and so now we have our choice to, from this square root expression, factor out the dy squared here. So now I'm looking at the square root, now dy squared, okay, and similar experience. After factoring out the dy squared, factor in the two terms here. First term here is going to become a dx over dy, but now allow me to start going skippy in the steps a little bit. Dx over dy all squared plus 1, because now we pulled out at the factor. Okay, and then there's a start to an end right here. Okay, and so you will start noticing where I'm going immediately at this point after getting some experience with the previous step. And so now that means I can pull this dy square outside of the square root, and of course going through the square root it gets reduced to just a dy. So my square root expression now is going to become the following. Square root of 1 plus, now I have dx dy, okay, all square remains inside of the square root, but now what I do here is multiply with a dy. Okay, and so now once again, let's hold on to the worry about the start and the end of our integral of our accumulation setup right here, but let's look a little further. The d expression here is indicating dy, and then let's look at this. Right now it appears to be the ratio of the two differentials, dx over dy, all square, and then doing that plus 1 inside the square root. But what have we realized here? Dx dy here means it's a derivative symbol. It's the derivative notation for treating x as a function and y as the variable. So that means first thing as a consistent point to check right here, this expression will be coming out in terms of y, consistent with this d expression. And then this notation is telling us further that it is our responsibility to re-express or to express this curve here. Whatever the started out form that it's given, but we have to express that in terms of y. In terms of y, we have to express our curve in terms of y to find that dx dy. And then once we have that, the problem here will be proceeded as an integral where we're as a definite integral where we're integrating in respect to y right there. So everything now is already in terms of y. So if everything is expressed in terms of y as a choice, then we cannot use A for start and B for ending. But our start and ending has to be on behalf of the vertical axis here on the y-axis. So it looks like the same curve, but it has a start at y equals c on the y-axis and ending at y equals d on the y-axis. So that means this is our final expression right here from C to D, and that is another expression. The same arc length derives into two separate forms depending on how you want to integrate it. So this here we want to integrate in respect to y, treating everything in terms of y. Okay, and so now really surprisingly that's enough general discussion. That's enough general discussion. Let's have a look into a couple of examples right here. All right, so let's have a look at our first example. So in example 1 right here, and my aim for this example here is also to get everybody, to get my students, to get the viewers, get comfortable with the way how these kind of problems are being worded out there. Okay, that's one thing, and then we will learn some experience about evaluating these, and we also experience a little bit of how challenging for the work after we set up the integral. Okay, so let's get to it. So we are starting out by having a given curve. So all you see here, this is an equation, y equals x squared. We are given that equation. Okay, and so now the problem is stating the following: set up the integral. We got to learn to move on with the steps carefully. We set up the integral, and of course the definite integral. Okay, set up the integral to calculate the length, okay, of the curve. Okay, so when it's in practical situation, I tend to use the word curve over the word arc like that, but it's the same. It's just basically the arc length. So set up the integral to calculate the length of the curve. Okay, because this gives us a curve in the interval from 0 to 1. So as of this point, okay, the curve is given in terms of x. Okay, and so that means this interval here by default is the interval in terms of x. Okay, and so that's the question like this. We want the question the problem asks us, and pay attention to the wording. And that's why I said one of my main aim for setting up these examples is you get comfortable with the way you get to be exposed to the way how these problems are wording. So be careful with what it's wording. The problem here is asking us to set up the integral, but did not really ask us to go all the way to the end and evaluate that integral yet. But set up the integral, the kind of integral that once we evaluate it, it will get us the length of that curve, of this curve in between 0 and 1 on the x-axis. Okay, let's have a picture. Let's have a picture. So, with my graphing calculator on decimals right here, okay, this is the graph for y equals x squared. Okay, that's nice parabolic curve right there, y equals x squared right there. But we don't want the full curve, we just want the part that's in between 0 and 1. So x equals 0 and x equals 1 is here. So in the end, we do have an arc restricting that between the 2 points on the interval. So I just now hid away the unnecessary parts outside of the interval. So just only in this interval right here, our arc is here. This bent little curve like that. All right, so we want to find out how long is that piece of curve. Okay, how long is that piece of curve? And so let's look at the setup of the integral. And so since everything by default, since everything is set up, everything is given in terms of x, and that is also in terms of x. Okay, then why not set it up? We made our choice, but it comes right out from what's easier for us, from what's already directly available or immediately available. Our curve is immediately available as an expression in terms of x, right? And then the interval is also in terms of x. Okay, and so in that way, let's set up. I will show anyone both. If this lesson is taught in a face-to-face class, I would do the same. I want my students to have that generality from the one same curve. Okay, and you understand because I pointed out that it's a choice that we're setting up. So the one choice is going to be a little more advantageous than the other choice like that. So here, let's start out with setting up the integral in respect to x. So in respect to x, then we do the following. Okay. How about let me make a note. In respect to x, or that means in terms of the x variable. Okay, in respect to x, then the formula becomes the following. L, the length, is the integral from 0 to 1. This is on the x-axis from 0 to 1. It's the square root of 1 plus, no, it's the dy dx. Okay. Many textbooks use the following version. It's the length from a to b of 1 over f of x. Okay, f prime of x all square. That version is okay too, but it's just me. I personally favor using the dy dx symbol because it gives me also a clear relationship that this is not only a derivative, it's also a relationship between the dy differential and the dx differential. And then this is here dx outside. So this is a setup ready for the integral that we are about to integrate in respect to x. But right now in respect to x, it's just a choice, and a choice that came out simply because our function is already given in terms of x. Okay, but watch out. There could be other problems where the function is given in one way, but the problem is asking us to set up the integral in terms of the other variable. Okay, in respect to the other variable, and that's why in this example, one question, but I want to show you two ways, two different choices, so you get comfortable to both. Okay, so in respect to x right now, then that's the starting idea right here. Starting point is at 0 on the x-axis, and ending of our accumulation is at 1 on the x-axis. Okay, and so in that way, all right, so on my other board right here, let's find out what dy dx is. We need to know what dy dx is to put that into our final formula setup for that. And so our curve is as a scratch word. Okay, our curve is given as y equals x squared. Yes, as I have pointed out already, this is a function. Y is a function, x is a variable, and so that means here we're looking at dy dx equals 2x. It's just simple work we have carried over from calculus 1, finding the derivative. That's 2x. All right, so now we are ready. All of a sudden, we are ready to calculate that the length of that arc. It's accumulation from 0 to 1 on the x-axis, where we go square root of 1 plus 2x all square with a dx. All right, and you can also write this as an integral from 0 to 1 with the square root of 1 plus 4x squared dx. But as far as setting up the integral, we are done. As far as setting up the integral, we are done. Okay, and so that's the integral we set up, but right now, that is in respect to x. Okay, so what about in respect to y as a different choice? Because we have to be, if you're studying with me, I have to prepare you for the best and also the worst scenario. And the worst scenario or the best scenario, I mean in those different cases where the problems gives you. Okay, so what about in respect to y? I mean, things might not come out as direct as how we integrate in respect to x right there. But see, our curve was initially given in respect to x, and the interval here is also in terms of x. So, but now let's write down the general setup for that, just the general setup. This is the integral. We're unsure the start and end yet. Let's just write it down, start to end like that. Because earlier I can do immediately 0 to 1 because I knew that this was on the x-axis. But now on the y-axis, we didn't spend time finding that yet. So let's leave it there as start to end. But keep in mind these are eventually on the y-axis. Okay, and then this is square root. I need 1 plus dx dy. Okay, all square. And then with a dy. And so again, just for anybody to know, so many textbooks will also have the version of the formula as following. Some c to d, 1 plus, now g prime of y. Okay, if you have expressed your function in terms of y. G prime of y all squared with a dy. Okay, so now, but I prefer using this differential symbol, this dx dy symbol. So now I am going to move on to the other board and let's do all the algebra work there. So here's how I see it. Our curve was initially given as y equals x squared. Y equals x squared. And so to find the expression in terms of y, we need to take square root and solve for x as a function of y. That's the common algebraic work that anyone learning at calculus should have gone through doing that in your algebra course right there. So this means we're looking at x equals plus and minus square root y. Now be careful. This is the part where you got to be careful over here. Algebraically, it is entirely correct to do this. Take the square root on both sides, plus and minus square roots. Okay, but because we're doing the correct work, we will end up with two expressions. I agree completely. Now we have to make our choice to rule away the one that we don't need. Because here there is actually 1x, but equal to two expressions. That means we're actually looking at two functions. One function is x equals positive square root of y. The other function is x equals negative square root of y. So we need to look for the appropriate one. Okay, and so let's have a look here. Let's have a look at the graph here, and that's what I meant. So this piece of curve, okay, this piece of curve right here was on the x-axis, in respect to the x-axis, then it's all the positive x-axis. See how the graph here appears on quadrant 1 right there, that piece of arc length? So that means now when back to the solved work right here, then we want x equals positive square root of y, because it looks like in the way how the problem initially indicated for us, we want x is positive or at least non-zero, because the interval for x on the x-axis is from 0 to 1. Okay, so we have to take that piece of curve that's consistent with x is greater than or equal to 0. So we chose this one. So we still have to do this. Plus and minus, and then we roll down the one we didn't need, and we select the one that we need appropriately. That's how it happens. Okay, and so now in that way, now I realize that now that curve that can be expressed as x equals square root of y. So that means I can optionally think of that as x equal y to the 1/2 power, because now I'm going to go ahead and find dx dy, our derivative of our function x as a function in terms of y. So now it's 1/2 times y to the negative 1/2. Okay, this is just calculus 1 memory coming back right here for anyone. So this means we're looking at 1 over 2 times the square root of y. That's the final reduced form in square root. Now for calculus 1 students, usually you are okay to end your derivative work right here as your final answer, but here I prefer to go one more step. I decide to go one more step, and I prefer that you can go one more step, because now writing the square root right here eventually will bring some benefits for the next step here. All right, okay, so here we go. We got our dx dy. So that means the length of that arc, that exact same physical arc can be found now by an integral from some start. So we haven't found the start and the end, so let's leave it there from some start to the end. But now it's a square root 1 plus, okay, the dx dy all squared now becomes a 1 over 2 square root of y all squared. And now it's completely in terms of y variable, and that's making it consistent with the d thingy here. It has to be a dy. Okay, so now we have our expression being from start to end, doing just a little algebra, and I still haven't found out about the start and the end yet, but this is 1 over 1 plus 4 y dy right here. Okay, and so with this setup right here, now let's swing over to the graph on the calculator screen right there. I mean on the computer screen. All right, so it looks like this graph here, these 2 points here, when x is equal to 0 on the x-axis, y value on the y-axis equals 0 as well. Okay, and when it's x equals 1 on the x-axis, y value also equals 1 on the on the y-axis. So from start to end, it starts from 0 on the y-axis and ends at y equals 1 on the y-axis. So in other words, now back to my problem, the integral setup is completely ready. Okay, it's an integral accumulating from 0 to 1, and that arrives as our integral setup. But this is in respect to y. In case anyone made this choice, right? In case anyone made this choice, okay, to integrate in respect to y right there. So why is there such a thing? Why is there such a situation about making a choice? Making a choice between integrating in respect to x or integrating in respect to y. Usually one choice is making the integral setup easier. Now you can see that we arrived at two different integrals. Completely different integrals. In respect to, I already erased in respect to x, but in respect to x, it was a square root of 1 plus 4x squared in the square root with a dx. Okay, and here we're looking at the integral from 0 to 1 of square root of 1 plus 1 over 4y. Somebody see this as the easier integral, somebody else seeing the earlier integral as the easier integral. And so that's why we have such thing as a choice right there. Okay, and so this is how it is. For example 1 right here, set up the integral, right, to calculate, and I showed two forms. One form is to integrate in respect to x, and the other form is in respect to y right there. Okay, and so now, before I'm closing down this part and move on to the next example, let me now make a remark right here. And so, how about I have to make it clear columns right here. So briefly from what we have done in respect to x right here, we have found it was an integral from 0 to 1 as a complete integral setup. Square root of 1 plus 4x squared dx. Okay, and that's the length, same length. And then in respect to y, as a different choice right here. Be ready for any case. Okay, then it's the length, it's the integral from 0 to 1, but it happens to look like the same integral bounds, but it's simply on different axes. Okay, this is on the y-axis, that's on the x-axis, so be aware about that. This is square root of 1 plus 1 over 4y. Okay, with a dy. So two separate expressions, two separate integral expressions that will give us the exact same result once we can calculate this. So the remark I'm about to say now is that I've taught this course for years and at multiple different places, different colleges and universities. So at some school, the way how the math department there, the structure their Calc 2 course. At some schools, arc length is learned after you have learned about some advanced technique to integrate. The reason I talked about advanced technique to integrate now is that in either way, either when you're setting it up in respect to x or setting it up in respect to y, okay, then it deals, your function is mostly inside a square root. You're inside a square root, you're inside a square root. And usually finding an integral, taking the antiderivative eventually, because according to the fundamental theorem of calculus, eventually when we get an actual value right here, we need to go through the antiderivative, the step to take the indefinite integral. Taking the indefinite integral on square root is usually a very challenging work like that. Okay, it goes from challenging to very challenging to the point of even extremely challenging that it completely remains impossible to find, where we have to turn over and use technology to get approximation methods to work. Okay, and so the remark I would like to say now is that, well, I prepared this lesson right here to aim at students who are learning calculus from an online course like that, where it could be I can deliver the same lecture here for students who are taking online courses from different universities or different colleges. So depending on where your course is structured, if you are learning about arc length here after you have learned some advanced technique where you can find a square root, where you can learn some technique how to find the integral of a function that has square root like this, then we can proceed. Okay, otherwise view my later part of this video after you have learned some advanced technique. The technique specifically I'm about to use here, the technique I'm specifically about to use here is the technique that's called the trig substitution. Okay, so in case your college structure the course that you learn arc length before you learn about trig integral, then go ahead and pause the video here. Okay, wait until you already learn what the trig integral is all about, then you're going to come back and view my later part. Okay, but then if you're taking class from a university or a college that structure your course to learn this arc length after you have already learned about trig substitution, then you can go ahead and view the following part of this example right here, because this same example I would like to push that into part B. So let's now call that part A. So, and for anyone who's ready, for anyone who's already learned about trig substitution, let's get ready for it. Okay, otherwise if you haven't learned that special technique, then go ahead and pause the video or even completely exit out. Wait until you've learned what trig substitution is all about, and then you can go ahead and proceed. Now, out of the two forms, I didn't have time to, when I was preparing this lecture, I didn't have time to particularly process through this integral carefully. So, but I have a method to handle that. So I'm going to stick with that integration in respect to x right here, even though both ways is going to come up to the same answer. Okay, so my point now is that part B of the example is the following. So we had one of the two setups here. So part B, in case that you are already ready, that you are equipped with that tool to calculate the antiderivative. So now we want to evaluate the length of the curve. All right, so now we get to that core point right there. So the worst scenario here is there are colleges out there who entirely skip some of the advanced techniques in Calc 2. It's what their decision is. We can't go anything against that. I'm only an instructor who teaches for them. Okay, but in case that you're a student taking class at a Calc 2 class at a college where in their structure of Calc 2 class they skipped out some of the advanced techniques in finding indefinite integral and leaving it impossible to solve this problem, then don't even worry about that. Watch for the case where it might say set up but do not evaluate your integral, meaning when you came to the end of part A earlier, then you can go ahead and stop, because likely if your instructor there skipped the covering over some of the special technique that's designed for this problem right here, then usually the kind of problem stops at where you can just say set up but do not evaluate the integral that calculate the length of an arc. Okay, and it's all due to the problem because square roots function is hard to find the antiderivative. Okay, and so now I'm really gonna find the square root. I mean the length of this arc right here. It is, and I'm using that choice integrating in terms of x. Integral from 0 to 1, square root of 1 plus 4x squared dx. So the special technique I talked about, if you've learned about that, then go ahead and you will understand. Otherwise, view my video, but or view my other lessons, or view your own lessons about what trig substitution is all about. But here I'm going to substitute. I'm going to let 2x. I'm going to substitute 2x for tangent of theta. Okay, and so all of that theory goes back to the formal lessons about what trig substitution is all about. So here 2x is going to be substituted by tangent of theta. And so in that way, x will equal as a function of theta. Now x is 1/2 times tangent of theta. Okay, and so that means I'm going to produce dx d theta as 1/2 secant square of theta. And so realizing that this is a quotient, a ratio of two differentials, dx over d theta. Now we can multiply the d theta to the other side. That gives us dx equals 1/2 secant square of theta times d theta. All right, and so in the end, it's a substitution problem. It's a substitution method. So I'm going to substitute all of this here, 1/2 secant square theta d theta for dx. This 4x squared is the same as 2x all squared, and 2x is substituted by tangent. Okay, and so again, I'm moving on with this problem, assuming that you have already learned what it means by doing a trig substitution. So if you haven't, like I said, exit out of this part of the problem, learn your lesson about the trig substitution formulae, and then come back and resume with this lesson here. Okay, but now here's how we can proceed in the next step, assuming you already learned about the trig substitution. This is going to be the integral. Okay, and then I'm leaving the bounds here. 1 plus, now 2, like I said earlier, 4x all squared is the same as 2x. 4x squared is the same as 2x all squared. So this is 1 plus tangent squared of theta. And then I realize I wrote this a little too large right here. Tangent squared of theta. Okay, and then multiplied. So dx is substituted by 1/2 secant square theta d theta. Okay, and so now let's look at the boundary here. So we had earlier that 2x equals a tangent theta. That's our substitution that we chose. And so when x equals and that means theta equals to tangent inverse of 2x. That's one thing we know as well. Theta equals tangent inverse of 2x. So when x equals 0 on the x-axis, we're looking at theta 1 equals a tangent inverse of 2 times 0. Okay, which is 0. Okay, on the theta axis. And then theta 2, okay, then we're looking at tangent inverse of 2 times 1. Okay, it's tangent inverse of 2 times 1. And that gives me tangent inverse of 2, which is some value, Okay, all right, and so in this case right here, now our integral starts at 0 for theta, but ending with tangent inverse of 2 for theta. All right, and so now this will become, so we have a known identity. That's 1 plus tangent square theta equals secant square theta. So we can use that identity for this 1 plus tangent square inside of our square root. And so it will become, so from 0 to tangent inverse of 2, okay, and then square root of secant square of theta, okay, which eventually will be just secant of theta times secant of theta here, d theta. So now our integral reduces down to the following, that equals secant cube of theta d theta from 0 to tangent inverse of 2. It's a value right there, 0 to tangent inverse of 2. Okay, and so now in that case right there, in my next step, so once again, it also depends on how your Calculus 2 course is structured, but at some point you will go through a problem, a lesson where it shows you how to find the secant, the antiderivative of secant cube of theta. And so here, in case you haven't learned, again, you can make a note here and just follow along with my video, and then once you learn about that formula, you will come up to that final, and you will have more convinced about that. But here, allow me to just tell you the answer. So tangent inverse, the antiderivative, the indefinite integral for secant cube of theta is going to be the following, because according to the fundamental theorem of calculus, we need to find the antiderivative of secant cube right there. Okay, and so all right, and I just now realized that by looking back at my notes right here, and looking right here at the step, I missed out that 1/2 in front, and it's 1/2 in front, and then the integral for secant cube is going to be, so now that 1/2 is there, but now it's going to be 1/2 secant theta tangent theta. Okay, and so this part inside of my parentheses here is the indefinite integral for the secant cube theta, and then this is going to be a plus, and then there's a 1/2 logarithm of secant theta plus tangent theta, okay, in absolute value. And then we're going to evaluate this from 0. So maybe I didn't leave enough space for myself. So that's 1/2, and then the 1/2 secant theta tangent theta plus 1/2 natural log secant theta plus tangent theta in absolute value. And then we're evaluating this from 0 to tangent inverse of 2. Okay, and so this function right here, this antiderivative, we're going to also multiply that 1/2 to each of these terms right here, which was already 1/2. And so now that's a 1/4 there, and so I'm going to step over to my computer station right there to grab the final answer for this. Okay, but it's something that's doable, but see, the square root here is not an easy thing to handle right there, even though we can do it, but it have to wait in case any viewer here hasn't learned about how to do trig substitution. Then you have to either you take notes here and then get yourself clarified once you've learned formally about the trig substitution that I brought up earlier. And then even we still face a little more challenge with this specific special secant cube of theta. So I gave the answer here, but you will find either through my own video lesson or somebody else's video lecture about how to find the indefinite integral for secant cube theta right there. But now I'm going to go ahead and evaluate this using a computer or a calculator. All right, and so accurate to 4 decimal places. This work right here gives me in 4 decimal place accuracy 2.9579 right there. Okay, and that's And that's the final answer. And so it's not a nice looking number, but it's a very challenging work to get that integral right here done. And so again, bottom line here is that, at some schools, when or depending on the teacher, you might want to watch out for the phrase where it says set up but do not evaluate the integral over here. Back to the problem where it's at back to part A a little bit. Usually, a lot of time there could be the problem after given the curve, okay, but the problem says set up, but do not evaluate, okay, the integral to calculate the length of the curve on the interval from 0 to 1. Okay, so that same problem right there, but for many instructors, watch for their, if your students with those instructors, maybe a lot of time they give you the problems such as you set up the integral, but you don't need to evaluate, because you can see that in part B of our work earlier, it was a challenging work right there, and it requires a lot of advanced techniques to handle. And in case your course is not structured to learn about the trig substitutions, or to learn about the secant square, secant cube, or in case you haven't learned secant cube, how to find antiderivative of secant cube prior to doing this kind of problem, then the problem will become very challenging, or to the point of impossible. And so watch out for that phrase that can save yourself a little bit, that you only need to learn how to set up but do not evaluate the integral. Okay.